I'm Rafael, and I work for Airbus Group, previously called EADS. So I was supposed to do a talk on Blue Code. So no, I'm not going to speak about Blue Code. I hope to do it at a later conference. You'll see the official statement from my company that so this is my employer's opinion, which is not exactly my own. And you had Thomas' statement. So here's the official one from my company. So we are discussing with Blue Code, and although the information in the talk didn't include any vulnerability, it does provide information useful to the ongoing assessment, security assessment of proxy SG by Blue Code. So once that work is complete, Airbus Group and Blue Code will jointly come back and share the research finding at a later conference in the spirit of responsible and safe disclosure to the community. So, this being said, we're going to speak about something else.
That's bullshit. That's just pure bullshit right there, Rafael.
I'm not going to...
I know it's not your statement, but yeah.
Thank you. So instead of talking about Blue Code internals, I'm going to speak about the challenges in designing a secure hard drive. So the talk title is less inspiring maybe than Blue Code, but we'll see, it may be interesting anyway. So the idea is to talk about external encrypted drives using hardware means to enter your secrets. So we're going to start with specifications, so what I'm talking about, what we are looking to create. We'll talk about design, so how do you create a secure encrypted hard drive that you use externally. And of course, the most important thing, if you're trying to design something secure, is to know how you're going to attack it and how you're going to evaluate the security of your product. So I'm going to spend quite a lot of time talking about attacks, and we'll conclude with a possible design. So the presentation goal is to give you a glimpse of the world of the consumer-grade encrypted hard drive enclosures. And so I'm not talking about defense-style encrypted hard drives. I'm talking about things that you can buy out there for cheap or quite cheap price. We would see what are the design challenges, how to balance security and cost, because if you're trying to design a consumer product, you don't want to have something costing like $500 just for encrypting a hard drive. Now, as I said, we'll see quite a few attacks and maybe possible solutions against those attacks. So, why am I talking about that? It's because I've done some thorough research on several hard drives enclosure at Airbus Group. So I broke a few drives. Unfortunately, I'm not going to give any brand name today. You probably understand that the first experience with Blue Code wasn't very great. So today it's going to be completely anonymous, no brand, no product name, and we'll talk later if you want. So some enclosures and also some USB flash drives that I analyzed were the input for this talk. So, what are we talking about? We're talking about external drives that should be using standard SATA hard drives. So basically, you got an enclosure with a USB port, and you put your hard drive in it, and then you get encryption. But in contrary to most hard drives that you can use with encryption, I'm not going to talk about the ones that use software on your PC to unlock the drive, but the ones that you have a hardware keyboard, for example, to input the pin, or a fingerprint reader, or RFID reader, as long as the input of the secret is done on the drive itself and not on the operating system. So you can have an optional LCD display for user comfort. And so the goal of course, of designing a secure hard drive is confidentiality. And so we're gonna see how we can work for that. And while you want confidentiality, you also want performance, because we're speaking consumer grade hardware, so you don't want to have something that is very slow, very secure, but very slow. So before I go on, a few words about vocabulary, because I'm going to speak all the times about microcontrollers. So micro C, you will see a lot in the slides, so it means microcontroller. So nothing very complicated there. Secrets. So I'm going to speak about secrets. Secrets means the data that you need to decrypt the files on the hard drive, to decrypt the hard drive itself. And I'm not talking about the files that the user stores on the hard drives. So when I'm speaking about secrets, think crypto keys. Speaking about crypto keys, I'm going to talk about the DEK a lot, the disk encryption key. So that's the key that is used mainly for AES to decrypt the data on disk. And one last vocabulary, one last definition, class break. Class break is when after breaking one drive, you're able to break all the drive very easily. So we'll see what it means later, but so keep those definitions in mind. So we know what we're working with, and we want to know what security do we need to make this kind of drives. So usually you want to allow multiple pins so that several users can share a same drive without sharing their passwords. So it's standard security practice, but it's not that easy to implement correctly. You want, of course, a good data encryption algorithm. So I put AES, XTS. That's kind of the state of the art for disk encryption, although it has some problems. Of course, for usability, if you enter a bad pin, the drive should tell you it's bad and not display you garbage when you access the drive, because it would be ideal, but it's not very user-friendly. More security features and anti-brute force. So if you enter a bad pin, you should have incremental delay, and possibly after 10 or 20 tries, you should have a full reset of the drive by erasing the encryption key. And last thing, you of course want to avoid the class break. So breaking a drive should not lead to the break of all drives. And our attacker model today is the one of a moderately motivated attacker who will do only offline attacks. So basically, you're thinking about someone stealing a drive or finding a drive in the subway or something like that. You're not talking about someone that will actively go and do an evil-made attack in your hotel room, or someone with more power that would go and actually hack you during the use of the drive, because it's way more complicated to protect against that. And of course, since we're talking about moderately motivated attacker, we're not talking about people with multi-million-dollar equipment like FIB that could be of help to attack the components we're also going to talk about. So we know we want a hard drive that you can use externally with a hardware keyboard, for example, with some security features. So we're going to see how we can design such a drive and talk about the standard design of such drives. So you start usually with a PCB, small PCB that you will put the drive on and use a USB port on it. And the main component that will be responsible for providing most of the functionalities is, of course, the USB to SATA bridge with encryption support. So you're not going to start from scratch. You're going to buy some of the available chips that you can find on the market. So it's just the result of a small Google search of a few components that you can buy that implement encryption and USB 3 to SATA functionality. So while most of those chips include a CPU, because you can customize them, you can change the firmware, you can run your own code on it if you want to change something. Unfortunately, they usually don't have enough GPIO pins to handle the keyboard, the LCD screen, and to handle all the functionalities that you want. So you're probably going to need a microcontroller on the side. And you're going to use the microcontroller to do keyboard handling and pin verification most of the time. So we're going to see a few designs using them. Sometimes you need to store more data alongside those chips. So you definitely will use an SPH flash to store, for example, the firmware, or to store optional configuration. Usually you will store the USB vendor, product ID, the name of the drive, this kind of stuff. And of course, you'll need a SATA port and a USB port. So if we will sum up the design with a nice drawing, you got the microcontroller on the left, which will input into which the user will input the pin. So once the microcontroller has verified the pin, it will get out the disk encryption key and send it to the bridge. Without the key, the bridge cannot decrypt the data. So usually it's the bridge taking the key from outside, and once it has the key, it will transparently decrypt the data and encrypt the data from and to the disk. So there are other designs we'll see later, but that's basically the principle of it works. Of course, you have the flash, SPI flash to store bridge firmware or optional data. So from there, you of course have to store crypto and store crypto secrets. So the problem here is we have a trade-off. Of course, we must be able to tell the user that the pin he entered is not correct. So we need to be able to do that. So if we can tell if the pin is good or not, at some point the attacker can get into the secrets we stored and do the same. So if the attacker is able to say, okay, this pin is good or this pin is bad, then he's able to brute force. So we have a trade-off here that we must be able to check for the pin, but it means the attacker can also check for the pin. So we have to find a way to prevent the attacker to get to the secrets so he cannot brute force the pin or get the key. So the basic design principle that you apply to crypto are, of course, in use there. So the disk encryption key should, of course, be generated by a cryptographically secure random number generator with a post-processed output with a hash function, for example. So that's, of course, basic. The pin should be hashed securely, so ideally with a slow hash function with a salt, so we'll get back to that later. And you should never, of course, store the encryption key in plain text in the memory, in any memory. So instead of storing the encryption key in plain text, you just, for every user pin, because you can have multiple users, for every user pin you use the hash of the pin to encrypt the disk encryption key, so that the attacker has to find the pin to decrypt the encryption key to access the data. So we'll review some designs, but we have to keep in mind that the main goal is to force the attacker to use expensive attacks. So we should not store the secrets on the disk, because accessing data on the disk is the easiest way for the attacker to get it. So we'll see some designs that fell in this regard that were actually seen in products. So the first bad design that we can review is this one. So it's the standard design that we've seen before, but we're talking about storing secrets now. So instead of storing secrets, for example, on the microcontroller, here the secrets, so I mean by secrets, the encrypted keys that will be used to access data on disk, clear text data on disk. So the secrets here are stored on the SATA disk instead of the board. So of course, that's not good. And the potential consequences are, depending on the way which secrets are stored and in the way they are stored, it can be catastrophic or not that bad. So the first case is, of course, if the disk encryption key is stored in plain text on the disk itself. So it's basically giving a lock safe with the key to the attacker. So it's game over. The other way is to store the disk encryption key with a fixed key. So basically, you have a fixed key in the microcontroller firmware that will decrypt the disk encryption key and then allow you to access the data. So every single drive will have the same key. So you only have to break one drive, retrieve the key from the microcontroller, for example, and then you will be able to access the data on all the drives that use this kind of boards. So that's a class break and an easy one. You just have to get the keys, the fixed key from the microcontroller. Another possibility that is really bad too is the disk encryption key is encrypted directly with the pin and stored on the disk. So if you know how it works, you just have to read the encrypted DEK and brute force the pin to recover the DEK and access the data. So it leads to a class break, because once you have understood how it works, you only have to have the same brute force tool to attack all drives. And the last case, which is the only one that's not that bad, is when the DEK is encrypted with a key that is generated randomly but stored on every board. So instead of having a fixed key, the microcontroller generates a key, encrypts the DEK, but stores it on the drive. So you really have to break the board to get the keys that encrypts the DEK to break the drive. So better store everything on the board then. So we have an idea of how to design the drive. what are the challenges? So storing the secrets, for example, and we'll review the different attacks and evaluation methods that we can apply to see and avoid doing mistakes on designing a drive. So to remind you of the attacker's goal, of course, the attacker's goal is to access the data on a stolen or found disk without the pin code. You find a drive, you want to access the data, that's the attacker's point of view. The ideal case is a glass break, so you only have to break one drive and you break all the drives. So I'm going to describe the few methods that I've been working with, from obvious and cheap to complex and expensive. So first, as a software reverser at the beginning, it was my first dive into hardware security. So if people are into hardware security, sorry for the mistakes I will probably make. So I started with software attacks first because that's the one I know, and went to the hardware last. But before we go into very advanced attacks, there are very, very basic things that we can do and test without any complicated setup to make sure the drive is not completely stupid. So the first one is very easy. You just take a drive, you configure encryption with a pin, you write zeros on the disk once it's configured. Then you remove the drive from the enclosure and you read data directly using a standard USB SATA bridge. So in theory, you should have encrypted data and nothing that looks like zero. So basically, you just want to check that the drive seems to be doing crypto correctly. So by verifying that the entropy is very high and just that ACB, for example, the bad block mode of IES, for example, is not used. So unfortunately, some drives use AES ACB, so older ones. And so it's very basic check, but you have to do it first. Then you want to check that the drive actually generates a random key and doesn't use a fixed key. So that's very easy too. You just take the same enclosure and you try to reset encryption. So if the drive is correctly designed, if you reset encryption by, for example, doing a factory reset or disabling or enabling encryption, if the drive is correctly designed, it should generate a new random key for encryption. So by setting a new pin after a reset, you can check if the key is the same as before. So you reconfigure encryption with the same pin, you write zeros. Once you've wrote the zeros, you take the drive out of the enclosure, you read the data, and you compare the data from the one you read in the first place. So if the data is the same, then the key is fixed. So it means every drive has a fixed key, or then you can compare with another enclosure to see if all the drives have the same key. So that's bad. Another very interesting test that I've actually seen in a product is to verify that the disk is tied to a specific enclosure. So you put the drive in the enclosure A, you configure the encryption with a pin you choose, you write some data, then you take the drive out of the first enclosure and you put it in a new out-of-the-box enclosure. Then you verify if you can access the data or not. In theory, since you've configured encryption, the second enclosure should not be able to tell anything about the drive. But sometimes you can see that the enclosure actually works perfectly, and if you enter the PIN, you access your data that we've written just before. So it means what? It means you take the first enclosure, you configure something, you get encryption, so it's theoretically secure, nobody can access the data until it breaks all the secrets. Then you put it in a new enclosure, never used before, and your drive works. You can access the data after entering the PIN. Okay, something's wrong here. It means everything needed to access the data on the drive is stored on the drive itself. So you need to check where the data is stored on the disk. In our case, it was in the end of the drive. And if it's encrypted, stored in plain text, if you can get the hashes of the PIN directly, well, you can check basically if it's total shit or not. So in my case, it wasn't total shit because it was encrypted at the end, but you really know that if you manage to recover the way to decrypt this data, then you will be able to do a class break because, well, if a new enclosure can read the data, so you can. So we're going to see now the typical design that is not totally bullshit. So instead of storing the secrets on the disk, as we've seen before, you store the secrets on the microcontroller or on the bridge, but most of the time on the microcontroller. Using this design, you can get started and work on something more secure. Since the secrets are stored on the microcontroller, accessing the secrets is basically accessing all the data on the microcontroller. So I don't know if many of you are familiar with the way microcontroller works, but basically they're just small CPUs with internal memory. And to protect against copyright infringement, generally, you have a way to protect the microcontroller so that you cannot read the code and data back from the microcontroller once it has been programmed. So the manufacturer programs the microcontroller, then he sets the fuse bits to protect them, and you cannot read the data back without resetting the whole microcontroller and erasing all data. So if we store the secrets on the microcontroller, you want to make sure that the microcontroller is secure and that you activate the protection bits. If it's not protected, then it's game over. You just have to use the standard protocols that are in place to access the data, and you can read the secrets and the code from the microcontroller. But almost nobody does that. It's always protected. And accessing the data on a protected microcontroller is actually a well-studied problem, so I'm not going to go into details. I've put some references at the end so you can check by yourself. It's very interesting. So there are quite a few attacks, like for example RAM access, where you will inject code while the microcontroller is running. So we'll not be able to access the code that is stored in the microcontroller or access the data, but some older microcontrollers could still allow you to read the RAM. So you would boot the microcontroller would store secrets in RAM, and you would be able to read the RAM. Also, usually the microcontroller is protected using blocks, so you can have blocks of code, and you can reset the protection by erasing blocks. So sometimes you can do something like a bootloader attack where you would erase the bootloader, rewrite the code, and extract everything by running a small leak data code on the serial port. So I encourage you to read 2 and 3, very interesting. And at the end of the scope, you've got the hardware attacks that mean that you will go and physically attack the chip. I'm going to go back on that later. So if you want to access the microcontroller, you can do it for 2 ways, for 2 reasons: for accessing the secrets and also for accessing the firmware. Because accessing the firmware is very interesting to understand everything about the security of the drive. So there are several ways you can access the firmware. The easiest one, it's not going to give you the secrets, but it's going to give you the firmware code, and it's very interesting, is to, of course, check the firmware update code from the manufacturer, if there is any. And sometimes you will find here the code in clear text, so you just have to load up the file in IDA and go start reversing. By the way, reversing PIC, for example, is a pain in the ass. So the next step is when the code of the microcontroller is stored not on the microcontroller itself, but on an SPI flash on the side. So the SPI flash is very, very easy to dump. You just take a bus pirate or standard reader, and you plug it to, and you read it. So if the code is unencrypted on an SPI flash, you just read it and you can load up in IDA. Then you got the unprotected microcontroller. You just use the documented methods to read it out of the controller, and that's it. And then things get harder. As you can have the encrypted code on an SPI flash, so unless you manage to get access to the key, you're not going to be able to read the code. Or you can try and hack the protection of the microcontroller. So depending on the model, if it's old, it's probably doable. If it's recent, it's gonna be hard. You cannot bypass the protection generally. And the hardest is when the code is in a protected, secure microcontroller. So when you get to the firmware, you want to reverse it. But what for? Of course, the first thing you want to check is backdoors. For example, if you've got a drive with a hardware pin pad and the code is locked in a microcontroller, the manufacturer could be tempted to put a magic password that will let you access the data without any problem. So that's the first check you want to do. And of course, then if there is no backdoor, you want to check the crypto mechanisms to make sure everything is done correctly. You may want to check if there is some key recovery scheme. So for example, if the drive is really made for consumer, you may want to escrow the disk encryption key by encrypting it by the public key, and the manufacturer would have the private key to decrypt the disk encryption key. So it would be useful for user support, for example, oh, I lost my password, I can't access my data anymore. So you would send the drive to the manufacturer, who would decrypt the data using his private key. And you may want to check also the way pin changes are handled. So if you change the pin, you may want to make sure the key is never written in clear text anywhere. And then, of course, you want to see how it works. Secret storage, verify that the anti-brute force protection is not completely stupid. You want to bin diff different versions if they are available. And also, you must reverse the random number generator, because there are two main things you want to check regarding random numbers. The first one is to verify that when you enter your first pin, a new key is generated. Because if, when you enter the new pin, no new key is generated, it means you're going to use the key that the manufacturer put into the drive. So potentially, the manufacturer keeps a list of all the keys that it installed into all the old drives, and then if you never change it, it's going to be able to access your data, and that would suck. And even better for the manufacturer is to create a flawed, predictable random number generator, because if it does, then it has a backdoor with plausible deniability. If the entropy of the random number generator is low, then you can brute force all the possibilities from the random number generator to get the disk encryption key. So the manufacturer can say later, oh, I didn't know about cryptography, and so I did just a basic random number generator that happened to break all the crypto, but I didn't know about it. And of course, if you manage to do that, you can reconstruct the attack and do an RNG attack. But that's great. That means you have access to the firmware, and once you've reversed it, you know everything about the drive. What about the case where the microcontroller and the bridge are protected correctly and you cannot access the firmware? Then you'll have to go and do black box reverse engineering. So one of the ways to do that is by sniffing the bus. So you want to understand the interaction between components. For example, you want to check the communications between the bridge and the microcontroller mainly, or between the different chips and the flash memory to see if there is anything interesting going on. And you do that by using a logic analyzer. So I'm going to give you a very practical example of some work we did on a drive with a colleague. So it was a drive with hard-to-dump components, so we couldn't access the code for the bridge or the microcontroller, and everything was encrypted. So we were completely blind, and we couldn't understand what was, we couldn't even tell if it was the microcontroller or the bridge doing the pin verification. So we started to reverse things by plugging into a logic analyzer and tracing signals. We just directly saw that there was a shared bus between the bridge and the microcontroller that was also used to communicate with flash. So in practice, what does it mean? You just open the drive and you place your probes. So it was very, very useful that the bus was actually shared, because we could plug our logic analyzer directly on the SPI chip, and it provides for easy access. So we were using the SALIA Logic Pro 16, which is totally awesome and was cheap. It's $500 or something, and it's perfect. So once we managed to get the logic analyzer running, we wanted to see what was going on when we did boot and enter a pin. So the result is you've got two very distinguished blocks of communications. So on the left, you can see that when you power up the drive, the bridge is reading from the flash. So the SPI flash contains the bridge firmware. It's encrypted, so we cannot read it. But you can see that there is a very compact block when it's reading its code. And then once it's booted, it starts communicating with the microcontroller, and the communication continues until you have entered your pin code, and you see why later. So the logic analyzer is very convenient because you can export the data as CSV, and you can implement also your own protocol analyzer. And it was very interesting there because the proprietary protocol between the bridge and the microcontroller was, of course, non-documented, and it was very useful to be able to access the raw data, to write an analyzer and try to understand what's going on between the bridge and the microcontroller. Thankfully, it was rather easy to analyze, even in black box. We could only see what was going on. We could not see the code responsible for running this protocol. So it's using classical protocol stuff like preambles, type length value scheme, so acknowledgements. We could really easily understand who was sending what at what time. And in the end, after analyzing all the requests, we could see that the bridge actually requests the pin to the microcontroller, that the microcontroller asks you for the pin, so you enter it on the keyboard, and then it sends back not the pin, but the hash of a pin to the bridge. And then the bridge verifies that you entered a correct pin or not, and it tells the microcontroller, okay, tell the user he's got a good pin or a wrong pin. So in this drive, the microcontroller only serves as an interface to the user, and it sends back the hashed pin to the bridge that will do the actual check. So if you sum up the security analysis, you can say that the bridge checks the pin. Unfortunately, the hash function used by the microcontroller once you have entered the pin to communicate it to the bridge is non-standard. So we can create a brute forcer, because it would have been interesting to, we'll see later, create a fake keyboard and send all the possible pins to the bridge to try and break it. But since the hash function we didn't know, we couldn't replicate the functionality of the microcontroller. So basically, what we could conclude is the drive security relies on the security of the bridge. So we didn't finish the analysis yet. We hope to find a JTAG on the bridge and go and break it. So if you cannot understand and break it from analyzing, there are quite a few more options that you can use to go and get more insight of how the drive works. For example, I encourage you to read a post on Sprites Mode's website, where Sprites has done an awesome analysis that uses power consumption analysis, timing analysis to analyze a drive, and it manages to find, using those readings on an oscilloscope, how the pin errors count is handled, and also a method to reset the number of tries that the bad tries that you had in the EEPROM, and also a bad pin, an early bad pin detection. So you could actually reset the drive before the bad tries counter was incremented. So he managed to get away to get infinite brute force attempts instead of being limited to like 10 or 20. So it's very easy to read. I really encourage you to read it, and I'm not going into details because it's very well explained on his website. Other possible attacks are, as just mentioned, that you could replace the physical keyboard by a microcontroller. So if you manage to get infinite tries, you can try and break it automatically instead of typing all the pins by hand. And you just have to replace the microcontroller, the keyboard, with a microcontroller that will emulate a keyboard and emulate all the pins that you can enter. And then you have more complex things that you can do, which involve, for example, injecting fault on the microcontroller. So if you think about the way CrackMe, a basic CrackMe works, where you're replacing a jump GE by a GNE. So injecting fault in a microcontroller is basically the same. You're trying to find where the jump to a bad pin is happening, and then you're going to glitch, for example, the clock, to make the microcontroller skip the jump. So it's basically nopping a jump in hardware. So it's not very easy to do. Definitely, if you don't have the firmware code, it's going to be hard, but apparently it's possible to do it. And then, if everything I've detailed before fails, you have a last solution, the ultimate solution, which is going after the hardware. So if the secrets are stored in the microcontroller, you want to access the data in the microcontroller to get the secrets. And the best way to do that is the chip decapping. So the principle is really simple, the theory is really simple, the practice is different. So your chip is usually in a plastic case, and you want to remove that plastic case to access the metal layers that are inside. So you want to access the circuitry. So first you put the chip in hot nitric acid, which is very dangerous, and then it removes the plastic cap. Then you want to remove the protective metal layers that are over the fuses. So the fuses are the protection bits that I mentioned earlier that prevent you to access the data from the outside. So then you use HF, which is even more dangerous. And so it removes the layers, and you can access the fuse. So you want to reset the fuse, so you can use UV light or other techniques. And once you manage to do that without rendering the microcontroller unusable, if you manage to do that while keeping it working, you can then use the normal way to access the internal data, for example, using the external protocols. So you're basically removing the protections, accessing the fuse, resetting the fuse so you can remove the protection, and then you can read the data from the chip. If it's not possible to do it by just resetting the fuse, you can also read usually the data directly from the flash memory inside the chip, but it's way more complicated. And I definitely don't know how to do that. And I don't even know how to do the hardware decapping and everything. But this is interesting. Even if you don't know how to do that and you don't want to mess with acid because it's dangerous, you can pay some usually Chinese labs to do that for you. So you just Google for microcontroller reverse engineering or code recovery, and so I just put 2 references in the end, but they were just the 2 first Google results. And so I was interested in a particular drive, and I sent in 2 particular drives. So I sent quote requests for dumping the data, and basically, so it's not that expensive because for an easy older chip with no advanced protection, you can get a dump, a guaranteed dump. So basically, you only pay after they send you half the bytes of the firmware. So you're pretty sure that they managed to get the code and the data, but you cannot exploit it because you only have half the firmware. And then you can pay and get the whole firmware. So it's guaranteed result for $2,000 for an easy chip. And for a more modern chip with not advanced protections, but with some protections, it was more than $7,000. So it's a bit more expensive, but it means that if your drive protection relies only on the protection of a microcontroller, then the price of the security will be, for example, $7,000. Interesting. You don't rely on this kind of drives for very sensitive data. So to conclude, we can maybe design something that is a trade-off, a good trade-off between cost and security. So our proposal is to use a secure microcontroller, which means basically a smart card on a microcontroller and not a basic microcontroller like a PIC or something like that. You want to use something that is certified for common criteria. I know that most of you, if you know common criteria, think they suck, but actually for hardware, they are a good measure of the time that you need to access the data on a microcontroller, or the way it resists to fault injection, the way, things like that. So you want a secure microcontroller with a hardware random number generator and hardware countermeasures to protect against dumping. Of course, you want to include a secure firmware update mechanism to be able to fix bugs. Also, the core of the security remains the USB SATA bridge, because it's the bridge that actually does the encryption. So you want to make sure the EES implementation, for example, is really good. So the only way to do that, because the manufacturer is not ever going to give you the internals of the thing, is to go and check that the controller is certified, for example, FIPS certified. If you got a FIPS certification, you can be at least sure that the AES implementation is correct. You cannot be sure there is no backdoor that stores the key on the controller, but you will never know that unless you reverse it. It's very complicated. So, and you also implement good crypto, of course. And something that I didn't mention earlier, but you want to slow attackers down by putting everything in epoxy. So epoxy is not the final protection measure, but it slows down the attacker because you have to remove all the epoxy to get access to the chips and understand what's going on. Regarding the crypto, as I said before, the disk encryption key should be generated by a secure RNG and by post-treating the output of the RNG with hashing, so basic crypto. Then you hash every pin with a salt, and you encrypt the DEK with each pin. And to implement the pin validation, you have two ways. Ideally, to make the things more complicated for the attacker, you would use the USB SATA chip bridge to read and check a magic sector. So you basically have to do the whole chain, send the DEK to the bridge, read some data out of the disk to verify that the data was decrypted correctly. So if the data is decrypted correctly, you know that the pin was good. But it's a bit complicated to implement, and it's a bit slow because you need to read on the drive. So the basic trade-off is to write a magic in the decrypted DEK. So when the user enters a pin, you hash the pin, you decrypt the DEK, and you check that the decryption was correct by verifying a magic in the DEK. But unfortunately, this is not really enough, because since microcontroller CPUs are really slow, you cannot really hash the pin securely. Because if the attacker manages to get access to the secrets, it will be able to brute force the pin. And so the protecting measures that you usually do in this way is to do secure hashing, for example, using scrypt. But modern password hashing algorithms are very slow, so you cannot use them on a microcontroller. And so you don't want to use SHA-1 or SHA-2 or fast hashes, but you need to find a trade-off between the verification time and the way the attacker can break your thing. And then you can go further. You can do way more things that are going to be very, very annoying for an attacker, but at which cost? Because those measures are really, really costly usually. So you can, for example, do your own ASIC or FPGA to implement verification or crypto. So basically, the attacker would have to reverse your FPGA code or go into reverse engineering your hardware ASIC. So it's doable, it takes time, but you would have to pay a lot more to get your board to the user's end, so it's going to cost more. And an interesting feature that you can add that is not very costly but a bit hard to implement is tamper detection. So basically, if someone opens the case, the drive case, you erase all the secrets, and so the attacker has lost everything and cannot decrypt the data. Okay, so we covered everything. I hope it gave you a glimpse of the world of encrypted hard drives and that you enjoyed the presentation, particularly because I only learned on Monday that the Blue Code talk couldn't be done, so I only had 2 days to prepare this presentation. Thank you very much, and if you have any question, please go forward. And don't hesitate to go and ask me any question afterwards during conference. Thank you.
Thanks.